Hi everyone, today we're going to continue with acids and bases on Ka and Kb. This is titled Learning Objective 6.7, student able for a reversible reaction with a large or small K determine which chemical species will have large versus small concentrations at equilibrium. Now when we dissociate an acid in water, like acetic acid in water to form hydronium ion and acetate ion, we first write the equation. And then we write the Ka value. Ka is the equilibrium constant of the weak acid. So whenever we see the formation of hydronium ion, H3O+, we then use the Ka to express the equilibrium constant, which is a ratio of product concentration over reactant concentration. Therefore, Ka is equal to hydronium ion concentration times acetate ion concentration over acetic acid. And water is not included in there because water is a liquid with constant density. Now, with Kb, when we have a weak base like ammonia in water ionized to form ammonium and hydroxide ion at equilibrium, the formation of the hydroxide ion dictates the use of Kb, which is the equilibrium constant of a weak base, and written as ammonium ion concentration times hydroxide ion concentration, that of the product, over the reactant ammonia concentration. Again, water is not included in the expression. Now, if we have a comparison between a strong and a weak acid, in terms of strong acid, nitric acid, which has a very large Ka value, which is not published in the book, but with a weak acid, nitrous acid, the equilibrium constant is Ka value is very small. It is 4 times 10 to the negative 4. So in terms of dissociation, the strong acid HNO3 ionizes to 100%, but the weak acid only partially ionized. Therefore, for HNO3, equilibrium lies far to the right. For HNO2, equilibrium lies far to the left. Now when we write the reaction, then we can compare the strength of the conjugate base of the acid versus the base water. In terms of the strong acid, the conjugate base NO3 minus has less tendency to attract the proton than water. Therefore, in this sense, water is a stronger base than the nitrate ion. In terms of the nitrite ion, it has a greater attraction than water for the hydrogen ion driving equilibrium to the left. Therefore, the nitrate ion is a stronger base than water. Therefore, the conclusion is that the conjugate base of a strong acid is weaker than the base water, but the conjugate base of a weak acid is stronger than the base water. Try not to be confused between strength and concentration. Concentration refers to molarity, which is moles of solute per liter of solution. You can have a weak acid with high concentration or a strong acid with low concentration. However, the strength of an acid refers to the degree of ionization determined by the magnitude of Ka. The larger the Ka, the stronger the acid. And means the smaller the Ka, the weaker the acid. Now here's a table documenting the Ka values of various monoprotic acids, starting with hydrogen sulfate ion, then you go down to hydrofluoric, nitrous, acetic acid, all the way down to ammonium ion. You can notice that the Ka value is in a decreasing order. And we said earlier that the smaller the Ka, the weaker the acid. Therefore, this is organized by decreasing acid strength. Practice problem number 1. Predict the direction of nitrous acid reacting with cyanide ion to form hydrocyanic acid and the nitrate ion. Now here we have the Ka values listed for HNO2, 4 times 10 to the minus 4. For HCN, 6.2 times 10 to the minus 10. And you realize that the Ka value of HNO2 is much greater than the Ka value of HCN, meaning that HNO2 is a stronger acid with a greater tendency to donate the proton, driving the reaction to the right in a forward manner and the equilibrium to the right. Practice problem number 2. Rank the water, fluoride ion, chloride ion, nitrite ion, and cyanide ion by increasing base strength. Now, since these are the conjugate base of acids, so we go to the conjugate acids first, HF, HCl, HNO2, and HCN, and then document the Ka values. Now, as we know that the higher the Ka value, the stronger the acid, the weaker the conjugate base. Therefore, we can organize it in such a fashion that the chloride ion is a weaker conjugate base than fluoride, which is weaker than nitrite, which is weaker than cyanide ion, purely from the ranking of the Ka values. Now we put water somewhere in between the chloride and the fluoride ion because from the previous slide you may remember that water as a base is stronger than the conjugate base of a strong acid, but weaker than the conjugate base of a weak acid. Therefore, it's ranked between chloride and fluoride ion. To summarize what we have learned today, we learned how to write Ka and Kb expressions for the dissociation of a weak acid and a weak base. Remember, when you form hydronium ion in the dissociation, we use Ka. When we form hydroxide ion, we then use Kb expression. The conjugate base of a strong acid is weaker than water, and the conjugate base of a weak acid is stronger than water in terms of its attraction to the hydrogen ion. And we noted the difference between concentration in molarity and strength in acid as denoted by Ka, and that the strength of acid relative to the Ka values. I hope that you have found the video helpful. From the team of MLCA, we'd like to thank you for watching the video and hope to see you again soon.